Hi there. This is our RO video. This is a basic consumer model. Here's the brine seal. You can see the water comes in this end and how fine it is. Any particulate will plug these up. Also, chlorine will destroy them. This is just a little consumer grade one. You can see some scale forming on this end and particulate on this end of it. Commercially, these are about 8 inches diameter and 40 inches long. A little bigger unit, but they all work the same. Some of the terminology: the array is the layout of the modules. The stage is the vessels in parallel. Permeate is the clean water. That's what we're trying to make. Remove all the minerals out of the water. Recovery is rated in percent. It's the permeate going out divided by the influent. Ideally, you want 100% recovery, but that's not possible. You'll scale up the unit, and also the water quality will degrade. So usually recovery is somewhere 80% depending on the water. Water flux, this is the water that goes through the membrane. It can be cubic meters through square meter a day. It can be gallons through square foot per day. So basically it's how the water goes through the membrane. Water permeability, that's the water flux and pressure. Solute, dissolved ions, total dissolved solids. This is the whole part of the whole thing, concentration polarization. All these items up here pertain to concentration polarization. You bring your water in, the clean water goes through the membrane, and the dissolved ions or minerals are left behind. As the water comes out, you develop a layer along the membrane surface, which, if it gets concentrated enough, will start scaling. You'll build calcium, magnesium, silicas up. As this layer gets thicker, it will require permeability of the water to get through this, or it'll just start forming scale and plug up the membrane. So all the RO designs are based on minimizing this. You have your cross flow velocity, which is the velocity of the water, to prevent this. So there's various things done in these systems to keep this layer from forming. This is a basic RO unit. It's a 2-pass unit. This will be pass 1. You take the permeate from pass 1, go through a pump, VFD pump, and then you go through another RO module to produce cleaner water. The basic operation: you have the raw water comes in, you add your chemical feed, either bisulfite, get rid of chlorine, anti-scales, biocides. They're usually put in here. And you have a filter, which is absolutely critical. The tolerances inside the elements are very small, and they can plug up with silt. You come out this through a VFD pump. You need to control how quick this unit starts with pressure. If you hit this with high pressure quick, you'll damage the elements. It'll telescope the mesh or the filter spacer. It can damage the surface of the membrane. You take the concentrate from the first stage and you feed it to the second stage. And the key valve here is your concentrate flow control valve. This is never adjusted. Once you set the unit up, this controls your recovery rate. And I can also tell you how your unit's running. Say you have 400 micromole water coming in. It could be 550 micromole feeding your second stage, and coming out can be 1300. Probably getting pretty close to forming scale here. With these valves set and left alone, 1 week you may run 78% on the VFD and put out 150 pounds to get 100 gallons a minute. Next week you may have to run 80 on the VFD and 160 pounds to get the same flow, which tells you your membranes are starting to foul. Either you're getting scale or you're getting plugging going on. Out of the permeate, out of the first stage, it can be 9 micromoles. Now the second stage, it could be 12 because you have higher concentration of minerals in the water. It goes to VFD, you have 10 micromole feeding the first stage of the second pass. You'll have like 0.7 micromoles permeate, which is fairly clean water. The drain concentrate can be 62 micromoles, which is really very clean water. This can be put back into the suction. There's really not much point throwing it away, but I guess that does happen. The basic membrane, it's a very, very thin layer. It's on top of polymetric support, and there's a fabric backing to give it strength. So this is very, very thin. This is where it can be damaged quite easily from scale particles, the mesh moving across this. That's why you don't want to slam these things with high pressure. You got to be really careful about adjusting flows. Here's the actual membrane construction. It's called a leaf. You have two of these together. So you have your membrane, and then you have the permeate carrier in between. This carries all the water that's collected. This is your mesh, your feed spacer. It looks kind of like a netting, but it's actually designed to maintain a water flow across the membrane surface. So you can see particulate will plug up this small area in here. That's why super clean water is important. Or you can get scale buildup in here, or biological growth. So this is really critical to maintain good flow through here and minimize particulate. Some problems, most membranes can reject between 98 and 99.4. That's kind of a rough estimate. Recovery somewhere around 80%, depends on your water coming in. You cannot have any chlorine. Chlorine will destroy this. The free chlorine will destroy the fabric and the membrane. You might have a rating of 2,000 parts per million per hour on the membrane, which means you can use 2,000 parts per million of chlorine for 1 hour to destroy it, or 2,000 hours at 1 part per million to destroy it. So they're very susceptible to chlorine or any oxidizers. Filtration is required. As you can see, we can plug up stuff quite easily. You may need anti-scale. You probably will need anti-scale, especially the more efficient units. Back in here, you're going to get scaling. This is going to be the higher concentrations from your concentration polarization. This part of the filter, you'll probably pick up dirt. If anything, any dirt coming here is going to plug up this end. Scale is going to start forming here, working its way back. Temperatures affect water quality. You'll see in the summer you'll have lower permeate quality. The theory is temperature expands the membrane pores, so they allow a little more ions through. The higher the pressure, the cleaner the water. The membrane allows so much ions through, and if you get more higher pressure water, you push more clean water through, so it kind of dilutes it. This pretty much the first part of this is a quick overview. We have a cheap home consumer membrane we've taken apart. As you can see, it's plugged up with dirt. This one happens, you don't have good filtration. You have your mesh, which is really very fine and small. Yet there's little spaces in here, lets the water through it. This is the actual membrane. There's 2 layers of membrane. You have 2 layers of membrane, then there's your permeate carrier in the middle of it. So it's the membrane surface here with the spacer. The edges are glued together and sealed, so it makes a leaf. So this whole thing is one. All this water is directed back into the collection tube. So you can see this membrane's had a lot of problems and it's pretty well destroyed. Back here it's been damaged pretty severely. Form scale. So the basic thing with ROs, you don't want to form scale in the unit. That's why recovery is limited. Use anti-scales. That's why you're using taper. To maintain water flow, you'll have 3 here and 2 modules here, and these may have only 6 elements. These may have 7 elements. So you provide enough cross flow velocity to limit concentration polarization to keep from scaling. So the whole design of these works for a certain type of water. If you change water, you may have problems with the RO. It's designed for certain water flows at certain micromole or conductivity concentrations of dissolved ions. So if you go from well water to river water or vice versa, you could have problems with them. They're fairly complex, yet they look fairly simple. And that concludes part 1.